So for many students, the area formula for a circle, pi r squared, is a bit of a mystery. We start area with a square, and we move from there to a rectangle and a parallelogram and a trapezoid and a kite and a rhombus and other shapes as well. And we can see a connection between the square and all of those shapes. And that connection is that we're measuring two things that are perpendicular. We're taking the product of those two perpendicular measures, and sometimes we have to mess around with it a little bit. 1/2 diagonal 1 times diagonal 2, for example, for a rhombus or a kite. But it's always traceable back to a square. This seems less connected to that. In each of those cases that I mentioned, it's one perpendicular measure times the other. Not so here, right? Radius. Well, certainly the radius is not perpendicular to itself. But what we're going to discover here in the next few minutes is that, in fact, it is directly connected back to the product of two perpendicular measures. We'll start with a regular polygon that is a triangle. That's an equilateral triangle, and hopefully you're familiar with the area formula for regular polygon, but if not, you'll see something here, and pause if necessary. If you are familiar, it's just a quick review. And so a regular polygon can be divided into the same number of triangles as it has sides. We just create the triangles by drawing segments from the center to each vertice. And so let's take a look at one of those triangles, and if we can find the area of one of them, we can multiply by the number of sides, and that will always work. There'll be the same number of triangles as there are sides, so we'll just focus on one of those triangles. And to get the area, we're going to drop a perpendicular from the center down to the side. And in regular polygons, that perpendicular from the center to a side has a particular name, and that name is apothem. And so the apothem is the measure from the center to the side, and we use that to find the area of the triangle. And then we can multiply the area of that triangle times the number of triangles, which equals the number of sides. Okay, so S, of course, is the measure of the side. And so if I want to find the area of this triangle here, AQB, then I multiply 1/2, area formula for a triangle, 1/2 base times height, so it's 1/2 S side length times A. Since there's 3 of those triangles, I multiply the area of one of them by 3, keeping in mind that that's the number of sides if I had more than 3 sides. Use a commutative property, and I'm going to take the 3 and slip it over here so that I get 3s. And so 3 times the side length in this case would be the perimeter. If it was a square or a pentagon, I would do 5 times the side length. And so we can just substitute that number of sides times side length in our area formula for the regular polygon and put in perimeter. The perimeter is the number of sides, in this case 3 times side length, so P. And so we get the area formula for a regular polygon as 1/2 perimeter times apothem. So let's take a look at regular polygons that have more than 3 sides. This has 3, of course, n is 3, so n is the number of sides. And here's my apothem. And I've added now r, the radius. And I call it a radius because every regular polygon can be inscribed in a circle. So you can see the circle here, but I'm gonna hide that circle again because we don't need to see it right away. So you can see I've got a lot of measurements here that are on display. The number of sides, 3. We're going to change that. The apothem, and I've got a lot of digits displayed, and you'll see why. But here it is. It's the green segment. The radius, as I just mentioned, right here, this heavy red segment. I've got the circumference of the circle. I hid that, but that'll come into play a little bit later. And the perimeter of the polygon. So the perimeter is just this number n, 3 times the side length, which actually you can't see here, but it is being measured. And in fact, the computer will just measure the perimeter of the polygon for me. The magic of the pause button. I brought the side length measure back into view here. And so, again, perimeter is side length times the number of sides. Some things I want you to watch. I've got both the apothem and the radius measures next to each other, these two lengths here, and I've got their ratio. So I took the apothem measure and divided by the radius measure, and in this case it's exactly half, and you can take a pause there and try and figure out why if you're unsure, but I'll leave that to you. Up here I've got the measurement of pi, or at least an approximation, and right above it the ratio of the perimeter of the polygon to the diameter of the polygon. So the diameter of the polygon, well, it doesn't make as much sense when there's 3 sides, but if I add a side and make it 4, you'll be able to see how that starts to make sense. So here I can see the diagonal with the circle in place. Okay, so the ratio of the perimeter to the diameter of the polygon, not the circle. Okay, so we'll want to keep an eye on what happens with these two numbers right here as the number of sides grow. Let's look at 5 sides. Let's look at more than 5. About 18 sides. Okay, so you can see these two numbers getting closer. You can see these two numbers getting closer, and in fact I don't want to watch these, I'm going to watch this ratio. So right now it's at 0.984, so it's getting pretty close to 1. Number of sides is 18, right? The circumference and the perimeter also getting close. Let's watch what happens as the numbers grow significantly. So what if I have 180 sides? Hopefully you can see, and I'm sure you can, what shape this is starting to look like, right? Look at the ratio of the perimeter to the diameter. Remember, this is the polygon, not the circle. 3.1414. Pi is 3.1415. Getting very close. It's only 180 sides. Seems like a lot of sides if you're in geometry class, but mathematically speaking, it's not a huge number. And take a look down here at the ratio of the apothem to the radius, 9998. Let's let this number jump, and instead of scrolling, I'm just going to type in 360 sides. So now I've got a 360-sided regular polygon. I've got this ratio of the regular polygon, 3.1415. So now we're the same to the nearest 10,000th. And the ratio of the apothem to the radius, 99996. Very, very close. So I created this model over here by reflecting triangles. There's 360 of them. That was a lot of triangles to create and measure and all of that. So what I'm going to do now, though, is let this number of sides increase further. Unfortunately, my model over here breaks down, but the mathematics over here is not going to break down. Okay, so I'm just showing, right, as you can see, it starts to look like a Pac-Man because there are no more triangles that are reflected. So that breaks down, but let's watch and see what happens as the numbers get bigger. And again, I want to let them get big fast. So let's look at 10,000 sides. Okay, so lots of 9s. We're getting very, very close. Up here, 3.141596, right? So 1, 2, 3, 4, 5, 6 decimal places, right? and that's only 10,000 sides. The beauty of mathematics is I can let this number grow as much as I want. And in fact, I'm going to make a bigger jump here and just say, what if we had 1,000,000 sides on my polygon? Now, my figure, of course, doesn't work at all. But take a look here, and this is really the key. The ratio of the apothem to the radius to the nearest 10 billionth, you can count the digits if you want, is 1. In other words, they're the same. 10 digits, they're the same. 10 digits, they're the same. In pi, the ratio of perimeter to diameter, the ratio of apothem to radius is 1. Okay, so we're going to go back and take a look at what this means, where I can show you some equations. Okay, so just a refresher about pi. Pi is defined, we accept this definition of pi as being the ratio of circumference to diameter of a circle, right? And so solving for circumference, I just multiply both sides by diameter, and then substituting twice the radius for diameter, I can get to 2 pi r equals the circumference. And let's keep in mind, what is the circumference of a circle? Well, really it's the perimeter of the circle, and in fact some places they don't even use the word circumference, they just use the word perimeter. Alright, so area formula for a regular polygon, remember, 1/2 perimeter apothem. Perimeter is the sum of the measures of the sides. Apothem is the distance from the center to the side. Okay, so if the apothem and the radius have this ratio, and we know it's not exactly 1, but to the nearest 10 billionth, that's pretty good, right? What happens as the number of sides approaches infinity? Well, then truly the apothem and the radius are going to be equal. And if the apothem and the radius are equal, right, then we can substitute the radius for the apothem in my equation for regular polygons. So instead of 1/2 perimeter apothem, I now have 1/2 perimeter radius, right? Remember that the circumference of the circle is 2 pi r, and so we can substitute also 2 pi r for the perimeter, right? As things got very big in terms of the number of sides, not only did the apothem approach the radius, but the circumference, the perimeter, excuse me, approached the circumference. So we can make that substitution as well, right? So we're going to substitute 2 pi r in for perimeter, 2 pi r. We have the 1/2 from the formula, and we have r for apothem, and so now all we need to do is simplify, and we get to pi r squared, the area formula for a circle. So when we look at r squared, r, of course, is itself, it's radius times radius, but we can take it all the way back through the area formula for a regular polygon and see that in fact really it's a substitution in this example of two things, of two measures that are really actually perpendicular. Not the apothem, but the perimeter, which involves the side length. And so that's how you get from a regular polygon to this mysterious but beautiful formula, pi r squared. I hope that helps you understand where pi r squared comes from.